Okay, everyone. Hello, welcome to our master seminar series. Professor Massimo Piccardi today and Inigo Jauregi Unanue, and Jonathan will do the introductions. Thank you for being here.
Thank you. So first, we have two speakers today, double header, so we're value for your attendance. So Massimo is a professor at UTS. He's been there for just over 20 years. And has had a prolonged career in computer science and information technology with many publications beyond NLP and other areas as well, and also many grants, ARC discovery, linkage, CRCs, you name it, he's done it. And really, his work recently in NLP has spanned a whole range of different areas. As you can tell, today we get machine translation and summarization, two key fundamental areas of the field. But also quite different. So we're really expanding a range of areas. And then we have, I'm going to do my best to pronounce this, Inigo Jauregi Unanue, who started off as a student, working with lots of at UTS, but has really been working in the field again for quite a long time, and continues to work with it now in RoZetta Technology, but also continue to be involved as an Edward Fellow at UTS. So both really doing exciting work in this field, and we'll hear a bit about it. Thank you so much for coming.
Thank you very much. Likewise. I wonder, should I hold the microphone while I speak?
Take it on the table. Thank you very much, Jonathan and Zana, for having us here. First of all, thank you very much, the audience. It's a great opportunity for us to have a chance to talk about our research. So we made our mind at some point what we were going to talk about to this audience, and we decided to focus our talk on the topic you see there, fundamentally how to train models for neural machine translation and for document summarization. So I wasn't sure about the composition of the audience, if they would all be familiar with NLP, so I put a brief introduction to the two tasks first. The tasks are very old. The tasks have been around in NLP. I think machine translation is possibly the oldest task of the entire history of NLP. Both have got this neural in front because, especially neural machine translation is often referred to these days as NNT, to simply mean that they've gone both deep and neural a few years back, and a few years back, we started about 10 years ago with the advent of deep learning. So these days, they're both based intensely, as models go, on large language models. But this is a misnomer, because what is large really these days is very ambiguous. Large is something like ChatGPT that has reached trillion parameters, whereas these models are a tiny fraction of that size. They're probably around like less than 1 billion parameters. By comparison, these are small models that you can run on your laptops. So quick, really instant recap of what translation is. Translation is obviously the conversion of text in a chosen source language to text in a chosen target language that should correspond. Instinctively, I would think perhaps is not such a difficult task because now you can use bilingual dictionaries, you can map words from one language, but there's nothing like word-to-word translation. Translation is much more challenging than that because of the enormous amount of cultural influence on how the translation has to be rendered in a language different from the source. So these days, models need fundamentally large amount of training data to be able to reach a performance that could be comparable to the human translators. The larger the corpora, typically the better. So that puts the situation is a bit like in these bullet points, there are language pairs that are rich in resources, and therefore the models are very accurate. And there are language pairs that are poor in resources, and actually there are many. There's supposedly 7,000 languages spoken in the world. So the language pairs that are still at a disadvantage, for which research is very, very limited, are actually many. And also specialized domains, where you don't have the amount of data that you can enjoy in normal general purpose language. That's about translation. Document summarization in the olden days was done in a very rough way by simply taking a document and starting to cherry pick portions of the document, putting them together to represent some kind of proxy for the summary, These days, instead, more and more, thanks again to these large language models, summarization is going abstracted. Abstracted means something much more natural, something much more like humans would perform summarization. Different from translation, one aspect which is quite notable when you do research in this field is that the so-called ground truth or reference, which is something human annotators undertake, is very different and can be very diverse as well. There's huge inter-annotator disagreement when, when you manually write down a summary for a document. So that's something you have to deal with. But the trend is somewhat similar, given that these models are large. If you upload a large training set, typically your performance would be better than for domains or languages where the performance is not where the data are not available. There's lots of other flavors of summarization, multi-document or cross-lingual, so there's a number of variants around the field. So that's just about the two tasks. So both of them, though, these days are still approached with these very well-known 6-to-6 models. 6-to-6 stands for sequence to sequence. Sequence to sequence here means that you have a sequence in input and the model produces a sequence at its output. These sequences are intrinsically of different length, and that obviously suits very well both the translation scenario and even more the summarization, where there's a big asymmetry, a large encoder and a small encoder by comparison. Now, the encoder is fundamentally, you assume that the input text is available at once. So the old encoders used to process text sequentially. These days, transformers do it parallel because there's no reason, since text is available, you can potentially process it all at once. But the coding is different. The coding intrinsically uses sequentiality. So you generate the conditional probability of the next word, previous words, and all the inputs. Unless, of course, you're trying, there are efforts here also to make the coders parallel, the famous non-progressive transformers, but performance is not yet as good.
For a question.
Yes, please.
What does encoder mean?
Encoder. Yeah, this block is one of the two main blocks of this sequence-to-sequence architecture. The encoder is responsible for taking text in input and converting that text from a sequence of tokens, say words or similar, and into internal numerical representations that fall the way, then through some mechanism called cross-attention, transfer depths onto the decoder for its code. It's a cascading model.
Sorry.
Yeah, please.
Is there like implicitly the assumption that both languages kind of work in the same way, meaning like the cat on the mat, the chaise sur le matelas, etc. Like has the same sequential structure, another language, or like actually the end of the sentence will have to be at the beginning or something like this?
So if you're talking about the decoder,
Yeah.
the decoder typically performs left to right. It's triggered by a so-called special token that could be beginning of sentence. So the prediction of the very first token is done based on that. And then based on this, there is a flow of information in the decoder, gets progressively unmasked towards the end of the decoded sequence. That's pretty much like saying the basic function involves transformers for text. So the fundamental quantity on the decoder end is this probability of the next word. So let's say that you have a slot T in the decoder, and you call Y the word across the entire vocabulary. You choose a vocabulary, say with, I don't know, 50,000 distinct tokens the system can choose from. And then at any one point, you assign a probability to all of them. These 50,000 tokens all get, like categorical variables, get one probability value, and then it's up to you what to do with that. You can just take the max and choose that word to the word at that slot. You can progress some path like viterbi styles, beam search, and the like. And that's how you pretty much obtain your output from the decoder for both models, for translation and for summation. And for the generation tasks likewise, please.
So the X's were the original tokens or these numerical quantities that you referred to?
So I left it a bit ambiguous. In notation, it could be the original quantities. In reality, what happens in between is like represented by this single character. Theta represents all the parameters that is we're talking about not those billion parameters that we mentioned before, plus the hidden states, recomputed from this data, the flow of them, all the weights, the internals are pretty much represented by this in a very abstract way. Yeah. So that's the fundamental quantity on the decoder engine. And so it's also the topic of training. So how do we train these models? No? The training or fine-tuning, depends how you want to call it here, is not unsupervised. This is done with supervised training sets, where you have a document that constitutes the input and a summary annotated by someone as the summary or some reference. So you need a supervised training set, X, Y, you need a loss function, a training criteria, because otherwise what you do is training set, and then you start looking to make your parameters such that they can minimize the chosen loss function. Universally, the loss function of reference is this quantity here, is the famous negative log likelihood, also known as cross entropy or vice versa, is exactly the same quantity. The cross entropy in the case of the decoder, T, is this quantity where you have ground truth token in slot T. You have the ground truth tokens previous to that in slots 1 to T minus 1, known. You have all your inputs, you have your parameters, and you try to find the values for the parameters that minimize this quantity. This quantity can be minimized, can reach 0 theoretically from a positive value in the case where your model is so capacious that you can give this variable, the token chosen by the annotator, a probability of 1. If that happens, the log is 0 and the entire quantity can go to 0. So this loss can be brought down to its minimum value only if you give a probability of 1 to all the tokens dictated by the annotation. Which brings up immediately this list of shortcomings, which are fundamentally the motivation for our work. The first is obviously if your data set is not big enough, the model is too big over T. No, just because. But I think more serious is the fact that you have this large vocabulary, again, for reference, say 50,000 tokens, and your annotator has chosen 1. During training, your model tends to assign probability of 1 to this, and says nothing about the other 49,999. There's no direction whatsoever. Are they all equally undesirable? Semantically, some could be similar, there are synonyms, lots of things could be done instead of just putting all your bets on maximizing the probability of the annotated token. And the last and obvious is the fact that this is a good training objective, but the evaluation is done with other metrics. So there's also a semantic gap between the evaluation measures and the training objective. So there will be something not optimal in that. There's plenty of qualifications, smoothing the NLL, regularizing other things, and reinforcement learning is one of the things I'll talk about in a few minutes. Last thing about the introduction is the evaluation. The evaluation is done in 2 fundamentally different ways. For both these tasks, the old way is to start matching, have your prediction, have the reference, start to match short sequencelets of words from the prediction to the reference, try to do these small matches of what's called engrams. There's lots of matches like blue, rouge, meter that use still this comparison of tokens. But the more important field is now relying on comparison of embeddings, numerical embeddings that are able to retain semantics, and therefore they are kind of more informative as measures than the original one. In typical evaluation, you'll find both, not just be sure that you capture both aspects. All right, so with that, briefly, our research is in this very space, is in document summarization, is in machine translation, and in particular in training objectives. We contributed both with training objectives that follow the policy gradient, which is a very well-known framework of reinforcement learning, and differentiable training objectives, which are alternatives to the log likelihood. Somebody called this objective engineering sounds a little bit pretentious, but it is what we're doing. I'll present 2 of our papers, and Inigo will present a third after me. The first one is this. We took a neural machine translation model, and we fine-tuned it using BERT score as the training objective. The score is one of these embedding-based metrics that I use for the evaluation of the generated text. The concept of the score is quite simple. If you know optimal transport is a general framework for comparison. The idea is that you have two sets of objects, weighted, typically objects, and you are trying to match the objects in this set with the objects in this set. And you try to find an optimal linear matching between them, so one object can be matched to multiple objects on one side and vice versa. So there's a kind of many-to-many optimal matching of the weighted objects in the two sets. The typical metaphor is workers and jobs, or the earth moving distance like soil and holes and so on. So best score is slightly different from optimal transport because it's not a many-to-many, it's a many-to-one mapping. So best score looks in, like for instance, given the prediction, your model, given the reference, looks the best match there, measures the amounts of match, accumulates it, and then returns as best score. Because there's not symmetric the role of prediction and reference, you can have a precision version, a recall version, and then you can combine them into a reference version. The score will look like something like this. There's the reference is here on the left. Excuse my hands. The candidate is the sentence here of 4 tokens. What we present to the briefing is the recall version. The recall version, so first you compute the embeddings of both sentences, and then you start to measure the pairwise similarity, something like a cosine similarity. And then for every token in the reference, you look at the token in the prediction that best matches it. Sometimes the match is not particularly good and records a lower score. Sometimes the match is very good and add them up along the sequence of the reference. This is the recall version. Like recall, like in classification, of how much of the ground truth your model has been able to do. And you can swap it and get the precision and similar. So because this is based on numerical vectors, it's completely differential. There are no problems here, not with computing gradients or this type of score. So what we did to fine-tune our neural machine translation model, in the end, is quite simple. The decoder here is a slot T, it produces these vector probabilities. As we said before, say 50,000 probabilities at slot T is the prediction of our decoder. Instead of picking the argmax or any other way to turn that token into a normal discrete token, we just keep the probability soft. We use it, we multiply with the embedding matrix in input to the burst score model, and we obtain an average embedding that is like, it's not a word, it's an embedding that will reflect the distribution of probabilities in the output vector. That's the vector that we produce as our prediction, that is the reference on the other side, the two embeddings are compared when the score is calculated. In this way, when we compute the burst score, we compute the gradients of this model. The parameters are frozen, there's no parameters update here, but the gradients backpropagate through these because there's no sampling or hard decision. Our maxim so is able to backpropagate and update as we want the parameters of the entity. So it's a way to be a bit creative around fundamentally. You can use the same trick to use any kind of pre-trained language model to backpropagate the gradients into a pipeline model of interest when you want to express some program. So we did that. Then the results are okay, but I'll show you in a minute. Just briefly also, just several ways in which you can create the vector of probabilities. One is to just take it straight from the decoder, another is to add gamma software sampling on top and a few other techniques that can control the sparsity. The results are here. Results briefly. There's some improvements in both the blue score and the F1 bell score. MS is another, just for measuring something else, at evaluation time. The mover score is an optimal transport, embedding-based measure. The improvements are not dramatic, and unfortunately, they're not always for the same version of our system. So these are different ways to perform the sampling. This tends to perform better, but has reached, in some cases, close to a percentage point of improvement in some of the metrics. The languages are 4 languages. The data sets are not huge, 200K parallel sentences by current standard, these are like small, medium size, just to give an idea. And there's also some interesting correlation between the sparser predictions seems to have performed better than the others on average. All right, so that's the first paragraph. Just before I forget, a final example for the data. I think the second example is compute. The NLL here is the model trained with a traditional training objective, the negative no likelihood. At some point, it makes a predictive mistake. Instead of this word, predict this or no was, which has a completely different meaning. With no offense for the singer. So the model that we train has been able to avoid that trap simply because it's been trained with an objective that is more semantic driven rather than just surface form driven or token driven. So being able to anchor to the real meaning and make the correct prediction. Obviously, we don't always get it right. Please.
I had a question about something you said. So you mentioned that the loss was differentiable. It's not, maybe I missed it, but you still have a maximization, like an max in the score, right?
Should I go back here?
Yeah. So for like that score, like that was defined with like computing the method. I think it's like before when
So the standard score is computed between two sequences of tokens, which are internally to the bus code model converted into embedding and later processed in this form. You can bypass the embedding, the first embedding layer of the bus code model, and directly enter one of the two sequences in the form of an embedding directly. And that's what we do. For our prediction, instead of a hard sequence of tokens, we propose a soft prediction, which is a sequence of embeddings that get compared with the embedding of the references and the bus code calculated. Differentiated, backpropagated, and parameters updated.
So yeah, it's not entirely. So you do find for each of the token the argmax in the corresponding sequence.
Oh, this is nominal max, is a max. Max, interesting, is a differentiable operator. This operator, the max, like a hinge loss, is totally differentiable. There's a discontinuity, but it's not a problem.
Okay.
Yeah. Good point. All right, so that's the first paper. The second paper is about multi-document summarization. Multi-document summarization is obviously the extension of ordinary summarization from the case we had just a one input document, we convert into a summary, to the case where we have multiple input documents at once in input set. What is the challenge? The main challenge is not just that obviously the input set on average will be much larger than a single document, but I think the biggest challenge is that these input sets are more maybe written by different authors, is more likely to contain internal contradictions, inconsistencies, and your summarizer has to make sense of these multiple documents and produce still a single summary. I think that's the main challenge attached to MDS, multi-document summarization. The first challenge, the size itself, is already a challenge because most of the current transformers are designed, including GPT, to deal with like sequences of up to 2,000 tokens, and those 2,000 tokens may not be enough for a case like this, where you have not many. Sometimes even there's a data set that has 100 documents in input set, short, but many. So to be able to manage most of them, we just use a so-called long format. A long format is just a variant of the standard transformer that decimates some of the dependencies in order to maintain a reasonable amount of memory all up, and is able to process up to 16,000 K tokens, which is close to what we need to do. Sometimes some of the input sets get truncated, bad luck. So when we started these experiments using just the standard events training objective, we noticed very quickly that the system during training was able to bring down the loss a lot by just focusing on one document. Pretty much the entire summary was coming from one document or two. And so we just intuitively said, let's try to address these. Let's try to create a training objective that will encourage the model to pay attention more evenly or democratically across the entire input set instead of focusing quickly on only one and get a quick return on the loss. It's a big challenge and also a big bet, because you don't know if by choosing this strategy to bias the training, at runtime your system will actually perform better with the same reference summaries. So it was not sure whether this will lead to better generalization than the standard NLL. So we just started, we took one measurement of coverage for single documents. We extended it to become a measurement of coverage for the entire input set. The input set, here, this is our prediction. This represents the document set and input set. We compute the coverage of our prediction with respect to each of these documents, compute a mean divided by the standard deviation. If this figure of merit is better than what the reference does, we give a reward, and then we adjust it for length. So that's our reward that is meant to reward the ability of prediction to uniformly predict or cover more properly across the entire input set. So the problem is that that's based on tokens. So we go back to the fact that that quantity is not differentiable. Therefore, we just use the policy gradient, which is a classic result when you have a reward that can be calculated, can be evaluated, but not differentiated. So you put your reward here for the scaling factor, and what you try to maximize is the probability to have high rewards. So this is our prediction. Our prediction is good into the reward. If the prediction is good from the reward perspective, the reward becomes big. And when you calculate the gradients and perform the parameter update, that has a big impact on your parameter updates. If the prediction achieves a reward of 0, 0 times whatever gradient, there's no parameter update. So it's the fundamental difference is that instead of putting grand truth tokens here, you are putting your own predictions. You are testing your models as you train it, say how good it is so far. Can it give me a good prediction already? If it gives a good prediction, you make a parameter update that rewards it. And you can do other things, like this one mentioned in the next slide. You can also use some kind of offset called baseline for a number of reasons. I mentioned them briefly, but you can also turn that into rewards and penalties. If the prediction is a poor reward, you can actually give it, instead of bringing the gradient, the parameters update towards that prediction, you bring it away. So you penalize that prediction. The problem with this type of training is that it's very erratic. When you look at the loss curves over the training iterations, instead of this nice decay of the NLL, you start seeing something much more jittery, and sometimes that can be a problem for convergence. So these baselines have exactly the goal to reduce. If the baseline is chosen wisely, has the ability to reduce the variance of the gradient updates and make them much more smooth, and convergence can be guaranteed. The problem is that if this is chosen arbitrarily, you can see very quickly that you pretty much change the gradient arbitrarily. In particular, it depends on the prediction. You can prove with an expectation in a second that your gradient on average is not the gradient of the unbiased gradient. And that could start again putting parameter update in a direction that is not reliable. So ideally, you would want both things. You would want an operator that is able to reduce the variance as much as possible by design, and at the same time have no bias compared to the original gradient without the baseline. And that's offered by this very elegant estimator, presented first by Tucker and then Grafgood, where the baseline is fundamentally obtained from an auxiliary neural network that you can configure the way you like, even just a simple feed-forward network, that will produce some kind of soft prediction that you subtract from the reward, use it as a baseline, and this will correlate because you can parameterize the network to minimize the variance. The network itself can be learned with another training objective to minimize the variance and obtain a very nicely stable operator. The two terms to the right, require a bit of calculation, of course, quite a lengthy explanation, I will not give it now, but those two terms are able to remove the bias. So this version of the policy gradient update, the very well-known reinforced with baseline operator, is debiased or unbiased and is very low variance by design. It's got both the properties that are required of these updates. And in fact, it performs quite well also in practice with more things It's quite quick to implement. It's just a lot of things to read, but not really difficult to code. So for the experiments, we experiment a couple of data sets, which are kind of now standard for the field. Bottom use, WCP, one has up to 10 articles per summary, a bit longer, the other has up to 100 articles per summary, but much shorter, like highlights. Coming to the performance, these are various versions of our model, and the performance improvement is just noticeable in some cases, and in particular in this data set. It's a bit more pronounced in the video metric, about almost like a percentage point. That's on the not news data set. On the other data set, the performance improvement is much more noticeable, it's been much more noticeable, and in particular, almost 3%, actually more than 3 percentage points in median metric. Introducing both the coverage reward that I described first and the algorithm that is used to train the relax estimator. So all up, it was pretty good story in a sense. The other thing that we observed is that these are the percentage of coverage of the input documents, 1 to 10 on average. You can see the green bar represents our model. Is much, much higher also for documents 8, 9, and 10 that instead tends to be kind of progressively ignored by the standard training. So we managed to achieve that stated goal of making the coverage of the input set more uniform, quite visibly. And it's interesting that that turned out in predictive performance that was not really disappointing in a sense. Just an example of things that is obviously is cherry picked. It's got a few things that are not present in the NLL, provide a summary, this fact here, a few other texts that the model has been able to extract from the input documents quite well. All right, so that's the remarks I'd like to say fundamental is this: at a parity of training sets, and a parity of models, spending time and effort to design more effective training objectives can pay off, but it's not a straightforward path. So I just don't want to convey the impression we can just do these, any hyperparameter works. No, there's a lot of work to make these training objectives alternative or complementary to the NLL, work better than the NLL alone. But if you put that effort, you are able to reach the kind of semantic gap between the standard NLL training and the metrics that are used in the evaluation of these tasks and generation in general. Relax, appropriable, an elegant estimator that delivers also the experiments. And through honesty again, through disclosure, the smaller the training set, the easier it is to make a difference with the training objectives alternative to the NLL for the usual stories that log likelihood is the ideal training if you've got infinite data. You don't have infinite data, so how much is much, how much is little. So the smaller the data set, these alternative objectives are like the build analysis that modify some of the limitations of the NLL.
Now we'll switch over. Yeah. I think they're part of the same slide and separate.
I think that's a separate, but you have, yeah.
I think we'll hold more general questions for the make sure we get the order.
So yeah, I'm gonna slightly change the topic, but not too much. So I'm gonna talk about a paper that was recently accepted at PCL, titled Translate and Test Transfer Learning for Cross-Lingual Text Classification, abbreviated to 3L, and it's been joined with Massimo and also RoZetta from Monash. So cross-lingual text classification, the task here is to classify text in many languages into the same taxonomy in a specific downstream task. For example, if it's natural language inference, it could be containment, neutral contradiction, if it's sentiment analysis, positive, negative, and so on. But this could be also the definition of multilingual classification, right? So the difference in cross-lingual is that usually the model or the classifier is trained in a source language that is different to the ones that you're trying to influence. And the reason for this is it's often not annotated or supervised data sets available in many languages, and you usually train it in a high resource language like English or Chinese or any other language, and then you test it in lower resource languages. So recently, the most common approach is also using large multilingual language models that are being pre-trained in an unsupervised way, gigabytes and gigabytes of text in multiple languages. Some examples are Embark, 25, XML, and they work pretty well. And the standard way of using them is what I just described, but train them in a supervised data set in a high resource language, and then at runtime, try them and see what's the cross-lingual transfer of these models, either in zero shot, so directly, or with a few shots of training in the target languages. But it has limitations too, its limitations. For example, if the model is trained in English, the cross-lingual transfer will be better in languages that are closely related to English, like for example, German, French, or European languages. But performance would be worse in more distant languages. Put as examples of Swahili type. Also, for very low resource languages, sometimes it's hard to train a pre-trained model because there is no even monolingual data available. So if you don't have even covered those languages in the pre-training, the performance also will be lower for those languages. Then there is also the curse of multilinguality. So some researchers have shown that when you train a multilingual model up to a point, the joint training of multiple languages can benefit the accuracy for many of those languages, but after a certain point, if you keep adding languages, the language interference comes into place and starts to affect the accuracy in downstream tasks. And what we suggest is also that the superposition of the language modeling and the task all in one model also it's a bit more challenging. If your model is limited in size, and so yeah, you have this capacity to learn both things. So a common alternative and it's been a standard baseline for years is to separate it into two different models, right? Like having a translator and then a classifier separately. And it's been a baseline for years. It's quite intuitive. So yeah, first translate it into English, and then you have classifier in English trained and European form. This has an advantage that, especially now with like time phase and all these like resources that the NLP community have made publicly available, you can quickly take that baseline, right? And have a good translator, download it, like have a good classifier, and test it. But it has its limitations too. It's on one hand, it's not differentiable, cannot really tune this end to end, has to be separately trained. And also there's the error propagation. If the translator gets a mistake, that gets fed into the classifier, and that error will carry to the end. So what we proposed in this paper was to recover or take this pipeline, but to make it end-to-end differentiable, so we can fine-tune it with few shots. The approach is what Massimo has presented before, like just a few minutes before in the version approach. Like we try to mix the probability distributions generated by the translator at each decoding step with the embedding layer of the classifier, create this average expected embeddings that can get fit into the classifier, and then we don't break the finisability of the network, and then we can train it. These are the questions like the same, expected embedding computation that Massimo has shown before. Alternatively, like if you make a hard prediction, you see you have an argmax, so we wouldn't be able to use that. We still use it for the next token prediction in the decoding step. So we still do the argmax for the input of the decoder, but yeah, then when we feed the generators the soft translation, we just do the expected embedding, and so this is tunable. There are some constraints or technical considerations. One is that because we are mixing the probability distribution of the translator with the embedding layer of the classifier, we need to have the vocabularies aligned. So we assign the probability mass to the right embedding. We have simplified this here in this paper, and we have forced both the language models to have the same vocabulary, at least on the decoder side of the translator and the encoder of the classifier. But it's something we want to explore more and try to remove that constraint in the future. And the other thing is that the number of trainable parameters is potentially larger because we now have two models. So if you're using the same model in both, which is what we did, you're going to have double-sided parameters that can cause, if you have memory constraints, that can be also a problem. It doesn't have to be to double the size. You can also have an asymmetric setting where you have a smaller model on one side or the other. But in the paper, we freezed half of the model because of the memory limitations we had. And so we only tuned the decoder of the translator and the encoder of the classifier, like focusing the training and the coupling of the two models and softening that connection. So go to the experiments. We carried out a bunch of experiments in 3 popular benchmarks. One XNLI is the natural language inference dataset, MLDoc, a news classification dataset, and multi-RLEX, legal document classification dataset, which is multi-label, so you can assign more than one label to the input text. And there are 20 languages, and these are the number of labels in each dataset. We use the MBAT model both to initialize the translator, the MTLM, and the classifier, and also multilingual language model baseline. So we use the same model for our T3 approach, the both modules and the baseline. Specifically, we use the model that's available in Hugging Face that's already been pre-trained to do translation, mainly to English, out of 50 languages. And we can use that model already as is in the translator, and just initialize it. And for the classifier, as usual in cross-lingual classification, we tuned it in the English dataset available in each dataset, in English training data. And then we tested in 0 shot and few shot 10 and 100. And as evaluation metrics, we use the accuracy and the mean R precision for multi-RLEX. And the code is available. So the results, this is the first dataset, the XNLI. Maybe we focus first in the average results. You see that our approach has consistently beat the baseline in all 3 settings, 0 shot, few shot. The good thing is that our main contribution, which is the tuning of the parameter at few shot, shows that can improve the performance of the T3L model. Here in this case, in average, over 1 percentage point. We see that for some languages, the difference between the models is not huge, like in Chinese. But in other ones, like maybe more lower resource language like Thai, you see that there is almost like 16, 17 percentage point difference. So for some languages, it can really show that if the pre-trained language model is not properly trained, maybe this approach is it's beneficial. There are also languages like here you notice Greek and Swahili, for example, that have very low accuracy in both models. The reason for this is that the MBAT that we use has not been trained for those languages, so it performs badly in both. The other 2 datasets, also MLDoc and multi-RLEX, similar trend. Maybe the improvement with few shot tuning of the T3 model has been bigger here. You can see that from 75 0 shot go to all the way to 82. But so has been also the one with the language model, and shows that maybe eventually, if you have enough shots, it might catch up, and a single model might be better. Maybe that's the case also in the multi-RLEX that eventually pass with 100 shots our approach. Then we thought, okay, for those 3 languages that were not part of the pre-training of the MBAT, can we maybe boost a bit its performance using some small dedicated translation dataset? So we took the IWSLP TED Talks data for those languages. You can see here the sizes of those data sets. They're not very big. 100,000 for Bulgarian English, 30,000 for Greek English, and Swahili 7,000. And so training the MBAN model further for translation in those small data sets, we could improve the BLES score. So improve the translation capacity of this model. And then we tested again the downstream accuracy in the translingual data sets. And we saw that there was a substantial improvement, like even using a small data set like this, 30,000, 7,000, it's publicly available and it's not in the same domain as the test classification data set. Could see, like, if you remember the table before, like the Greek was around 30 something, around those to 70, 72. So it was a massive jump with little effort. Of course, so the baseline can also be further trained with the same translation datasets. So to compare, we also improved the baseline. So we trained also the baseline over the translation datasets, and we also saw an improvement. So you see that in the case of the Greek language, it also jumped to over 61. But as you can see, that the improvement generally, at least in 5 out of 6 settings, was much bigger for our approach compared to the baseline. So this can suggest that, like, if you have a language that's challenging, that like there's not much data available for a pre-trained language model, it might be more efficient to, like, more cost-effective to have a translation data set and do this approach than maybe collecting monolingual data and training a large language model. So it's interesting and challenging. Yeah, this is some sensitivity analysis of like how good the translation has to be to obtain good accuracy. I guess it can change from language and from dataset. Like in the case of Spanish, after 25 like improving the translation didn't really improve much the downstream accuracy anymore. Then there's an example of the intermediate translations. So I said the intermediate translation is a soft translation in the PL pipeline, but we wanted to get a sense of how those translations change once we do the few shot tuning. We admaxed those probability distributions that we generate to have a representative translation, intermediate translation. And we see that with zero shot, the translation is correct, but the classifier still misclassifies this sample. And after the few shot tuning end-to-end, we see that the model starts to make some of these functional simplifications. So instead of saying operatives, so agents, which is the same word that's been used in hypothesis. And so the simplification, I think it's probably gonna have something to do with the correct classification at the end. And this is something that also been reported by Terry and others, where they use like reinforcement learning as an alternative way of doing this pipeline. There's another example, maybe I won't go into it. Then finally, some limitations. So inference speed, it's slower because now we are introducing a sequential decoding in the middle translator, and that's left to right. That's a bottleneck because we cannot parallelize it. And we saw like an order of magnitude slowdown in the top 2 datasets in multi-RLEX. For some reason, they haven't really explored why, but we measured dataset massive slowdowns. I think it was because the multi-label dataset, the larger documents, I have to dig into it a bit more. And then the vocabulary constraint is a limitation. At the moment, we need to have the same vocabulary in both models, and that limits a bit the models that we can couple together. What we want to do is to explore how we can take away that constraint, because ideally it would be good to plug and play any Hugging Face model together, like a translator and any other classifier that you want, and start really use this model in a single shot or few shot setting. So yeah, that's it. we presented this approach to generate self-translation from data, translate on this pipeline. Tunable, I think it's working quite well, especially for low-resource languages. And we extending this to other cross-lingual tasks like summarization. It's not limited only to text classification. And we also started to research how to address this vocabulary constraint. That's it. Thanks.
Thank you very much, both Inigo and Massimo, for a really interesting part. So we've got some time for questions. I have a question to start actually on this piece. You mentioned this issue as you add for languages in prior work, eventually once the grades. Have you considered trying things where you sample from a large space of languages, if you have available, based on, say, language families or syntactic similarity or other properties? And so, rather than using all the languages, use the one for the post import attach. Does that help? Or that's something?
Yeah, I think that helps. In the case of 3 languages that were not covered, one of them was Bulgarian, and but Bulgarian performance was still quite good. And I think the reason is there were languages in that set of 50 that are close to Bulgarian. So yeah, I think that it's a help.
But it's worth the sort of adding to also improve it, like maybe you leave out Arabic or something because it's has different qualities and so on.
Yeah.
So that's it. Come on.
I'm going to question, but I have to preface that by saying this is not my area, so that might be a completely naive question. So you mentioned one of the takeaways, if I understood correctly, is that instead of going to gather more data, you can just do that kind of cheaply by basically training on something else and then fine tuning. But at the same time, you've got that 10 times slowdown somewhere. So have you had a baseline, another baseline, which is like, well, here's what I just did on the available data, and how does that perform with I don't know how to quantify that, the comparable amount of time and energy spent to gather more fine, good quality data, and to see where the trade-off lies.
You mean like the effort of annotating more?
Yeah.
But I haven't really quantified that. But I think generally it's much more effortful to annotate, especially for test classification, where you can have any test classification like taxonomy, right? Like it can be multiple tasks, like sentiment, inference, like you can invent your own test classification answer. I think like it's more cost effective to annotate, if you want to annotate something, to annotate a translation dataset, because that can be reused for any test classification dataset if then you have a classifier in a high resource language. Like if you have an English classifier in the task of interest, you could annotate a small translation dataset and then try to leverage that classifier. Not you, I'm answering your question.
Yeah, but I was just wondering,
maybe one data point I can throw in. The last sort of data and live data acquisition project I did was it's called a classification form. We annotated about 80,000 lines of text with 200 hours of work, human work. So, in division, it's like expensive. Where you just throw it on computers and
one is a sunk cost, where the other is like you have to slow down
every time.
Yeah,
sure. Yeah. Computers are cheaper than people. But no, it's interesting. It's actually quite. We rarely do those trade-offs, right? Obviously, people talk about high speed versus your speed. There's no comparison with the data quantifying it.
And more like I'm also not a linguist. I'm not mapping. How do you choose the language in the middle? So my thing is that you translate to English and you use that. Or is there like a better language that more expressive that you could use that previously I don't know.
You mean why you use English?
Yes.
No. English, usually the main reason to use it is because there is data available to train the classifier. There is no other reason. There might be an easier language, and if it makes more sense, if your languages of target are closer to a different high resource language like Chinese maybe, then it makes more sense to have a high resource like a Chinese translation and then use Chinese model.
But there's no like universally better language that's less ambiguous, so that you can like Esperanto or whatever.
There might be also, I'm not a linguist, also, I'm more computer scientist, but I couldn't tell you exactly what is the best language to use in the meeting. It's the best people language, but I think English usually is the choice because of the hierarchy.
So checking online.
It's a bit of a tricky one, but going back to your talks, Massimo, that's probably not an easy one to answer, but were you able to do any sort of error analysis to maybe sort of characterize what kind of linguistic phenomena those two changes was good at, or you know, like what linguistic phenomena improved versus maybe got worse or stayed the same?
Yes, that's a very good question. Would deserve more analysis, not only of those I've been able to present, but also probably to carry out in the first place. The trade-off is quite intuitive in the sense that if you are using as training objective something that was the semantics, you're likely to have predictions that will score better in that particular property. If you stick to surface forms, you will do better in surface forms evaluation. So it really depends how you want to assess the quality of your output. We've looked at, in other work also we're doing now, we're looking at lots of other properties like fluency. We carried out a unit of work on adversarial attacks. You know, the adversarial attacks to text classifier are scrutinized not only in terms of effectiveness, but in terms of what they look like. So you have to look at grammaticality. So you can influence all these properties by training objectives that fundamentally target.
So, and then those are human ratings, so fluency and grammaticality as opposed to like an automated evaluation metric here.
Yes and no. I mean, you can do it two ways. The human way is expensive, the human in the loop, the reinforcement now, the human in the loop is obviously time consuming. You train these models, not like the famous, what's it called? It sounds like BERT score, but it's actually BART score. BART score is a encoder-decoder full transformer that is able to give scores under all these properties. It's being trained with human judgment, so there's still automated systems that are proxies, and you can leverage those for training.
Well, we're at time, so let's thank Massimo.